All right, 7.4, exponential growth and decay. If I can spell. All right, so first, still clearly can't spell, separable differential equations. So this is why I said the other day that one problem that you couldn't do that was in the packet that was like the slope field problem. Part of the problem, the reason you couldn't do it is because it had to deal with this. So after we're done with this, you should be able to complete that problem, if you will. So a differential equation of the form dy dx is equal to f of y g of x is called separable because we separate the variables by writing it in the form 1 over f of y dy is equal to g of x dx. And then the solution, so the way we actually would go about solving this, is found by anti-differentiating. This is a really long word. 19 letters, if I counted correctly.
What?
Each side. So we anti-differentiate each side with respect to it to its isolated variable. For some reason the book says it's thusly isolated variable, and I just feel like that sounds weird, so
Yeah.
that's why I paused, because I was like, what? I was like, thusly?
Okay. I thought
Thusly.
just with respect
I feel like
to-
I'm back into like the King James. So basically, we anti-differentiate like the left side with respect to y and the right side with respect to x, which is like opposite of what we would normally do. Normally, we would just be doing it like the whole thing like in one swoop, I guess, but not what we do with these. Okay, I am going to go ahead and do all the notes, I think, first, and then go back and start examples. Not a ton, but I just feel like it just makes the most sense to go ahead and do them all, and that way I can have a notes video in the future, too.
Okay.
So, let's see, the next thing, the law of exponential change. If y changes at a rate proportional to the amount present, so if dy dt is equal to k times y, and if y is equal to y sub 0, when t is equal to 0, then y equals y sub 0 e to the kt. And that makes sense, right? Because if t was 0, then that would be 1, because that would end up being e to the 0, which is 1, and then y would be equal to y sub 0, or y initial. So the constant k is the growth constant if k is greater than 0, or the decay constant if K is less than 0. We're going to have some formulas here, which you might recognize from pre-cal. Continuously compounded interest. So we've got A of t is equal to A sub 0 times 1 plus R over K times KT, where K is the number of times compounded.
So these are going to be like word problems?
Yeah, some of them. And T is the amount of time, usually in years.
Okay, so it's R over K and then KT.
Yes. If we did it in terms of, first let me just do a refresher. So if K said, or like if it said that it was compounded monthly, what would K be? 12. If it said weekly, what would it be? 52. If it's a daily,
365.
yep.
Or depending on it.
Yeah. We would typically say 365 unless for some reason they specify that it's a leap year. But they're not typically going to do that. I don't think I've ever seen a problem where they did that. Because obviously that only happens once in a,
Yeah. I feel like that's not
once every 4 years. You just happen to get an extra day of interest that year, I guess. So we can also do this, like instead of it being in like discrete intervals, we can add interest like continuously at a rate proportional to the amount in the account. And so the growth of the account with the initial value problem, we can have the differential equation, dA over dt is equal to R times A with the initial condition that A of 0 is equal to A sub 0. And so then the amount of money that would be in the account at that point would be for, if it was actually done continuously, would be A of t is equal to A sub 0 e to the RT, where R is the continuous interest rate. And they would have to give you that number. And it's usually given as a percent, and you would need to make it a decimal. For radioactive decay, y is equal to y sub 0 e to the minus kt, where k is greater than 0. And obviously, usually when we get into exponential growth and decay problems, we tend to see half-life problems. So a definition of half-life the half-life of a radioactive substance with the rate constant, basically just meaning it's not changing, or with rate constant k, meaning k is greater than 0, is half-life equal to the ln of 2 over k. And then we would use that formula to solve for the half-life.